We're going to begin today on the coast of California, in a place that has a lot of atmosphere. We, in fact, are going to start out by finishing up our discussion of atmosphere, and then we're going to be moving on to talking about how it is that the atmosphere influences what goes on in the ocean. And then we'll turn our attention specifically to water. So let's start by talking about atmospheric circulation. Let's begin our discussion by talking about convection currents. This is a topic that we've touched upon a few times in earlier episodes, but let's formalize this discussion. Convection currents are driven by differences in temperature. If we're talking about convection as it occurs in the air, it's like this diagram here. Sun warms up the ground heats up the air directly above it, and this then causes the air to expand, which is another way of saying that it declines in density. And less dense air rises. As it rises, it starts to cool off. And as it cools off, it becomes more dense and sinks. And so you get this circular pattern of motion, which we call a convection cell. Now, here's another picture with quite a bit of atmosphere. And so it gives us the opportunity to write a few notes about this phenomenon. What we notice is that geographic differences in the amount of solar energy reaching the Earth drives atmospheric circulation. So, for example, with respect to convection, air that's heated in tropical regions, equatorial regions, becomes less dense, rises, and heads toward the poles. As it approaches the poles, it cools, becomes more dense, and sinks, and starts flowing back toward the equator. A related kind of a phenomenon is wind, which can be defined as complex horizontal air movements. These are driven by a variety of factors, but one of the factors is actually the fact that the Earth rotates. Now, another circulation-related issue is that of the Coriolis effect. The Coriolis effect is something we're all very familiar with. Every time you pull a plug out of a drain and watch the water go down it, you are experiencing the Coriolis effect. But water is not the only fluid that does this. Air is also a fluid and behaves in this kind of a way. So in the northern hemisphere, the tendency is for fluids to turn right as they do something like go down a drain, whereas in the southern hemisphere, the opposite occurs. Now, phenomena like all of these are also related to the fact that the Earth has patterns of prevailing winds. In different parts of the globe, at different latitudes, winds tend to blow in particular directions. Let's take a look at a graphic of this so that we can see exactly what I mean. Let's turn our attention first to the tropical regions of the globe, and let's focus first on the trade winds. Note that they come out of the east and move toward the west in a direction that brings them toward the equator. In contrast, when you leave the tropics, when you get above 30 degrees north or south into the temperate regions, now you have winds that come out of the west and move toward the east. For those of us from North America, this is a very familiar pattern. We're familiar with our weather coming from the west towards us. And then as we reach the polar regions, both in north and south polar regions, again the winds come out of the east and move toward the west. So let's now start considering how it is that atmosphere influences ocean. Consider, for example, that the prevailing winds of the planet generate phenomena referred to as gyres, which are circular ocean currents. And these, as a consequence of the Coriolis effect, head in a clockwise direction in the northern hemisphere and a counterclockwise direction in the southern hemisphere. Let's move to another location on the coast now. Our last picture was on the coast of Northern California, looking at the Pacific Ocean. We're now on the coast of Rhode Island, looking at the Atlantic Ocean in the midst of these phenomenal rock outcrops that you see in certain spots on the coast of Rhode Island. These locations form a backdrop for us to talk about another oceanic phenomenon, the ocean conveyor belt, which is driven by differences in density of seawater. So, for example, the cold waters of the North Atlantic are also rather salty, and these characteristics make the water dense. The dense water sinks to the deep ocean, where it flows south, past the equator even, all the way to the coast of Antarctica, where it then flows along the coast and then starts moving up into the Pacific. On the other hand, in tropical regions of the Atlantic Ocean, we have the Gulf Stream, which is a current of warm, less dense, less salty water, which moves from these tropical latitudes along the east coast of North America. We even feel them here in New England, especially in late summer. The Gulf Stream can get rather close to us, and it travels to the coast of Europe, bringing this warm water with it, where it then cools and sinks and heads back south again. So let's summarize. There are phenomena referred to as gyres, which are circular ocean currents, which in the northern hemisphere move clockwise and in the southern hemisphere move counterclockwise. These gyres are generated by prevailing winds of different latitudes on the planet. We also have the phenomenon of the ocean conveyor belt, which is driven by differential density of seawater. The cold, salty water of portions of the planet are denser and tend to sink to the deep ocean where they flow, whereas the warmer, less dense, less salty water of portions of the planet tend to move along the surface of the ocean and can be involved in bringing thermal energy from tropical regions of the planet to colder regions, thereby distributing thermal energy about the planet in ways that it otherwise wouldn't get distributed. Now let's head to the western tropical Pacific, which is the birthplace of another major oceanic pattern. Notice the huge waves crashing against the rocks in this picture. Those waves are being generated by the trade winds that blow, if you recall, from east to west across the tropical parts of the planet. Well, during typical years, when the trade winds are well set up, this is the kind of phenomenon that you see. But periodically, the trade winds weaken. They start to break down on a schedule of maybe every 3 to 7 years. The trade winds will undergo this weakening. And then we have the occurrence of an El Nino event, more completely known as El Nino Southern Oscillation, or ENSO for short. When the trade winds weaken, all that warm tropical water, which is pushed to the west into the western Pacific, starts to extend east. And as it does so, it has a substantial effect on Earth climate. Let's take a look first at a graphic of what goes on during non-El Nino years. In the eastern Pacific, the coast of South America, what we see is that the trade winds blowing off the land and moving across the ocean keep that warm surface water pushed to the west. And that also results in cold, deep water upwelling along the coast of South America. And as that colder, deeper water upwells, it brings with it nutrients from the deep regions of the ocean. This nutrient-rich cold water fuels these ecosystems occurring on the coastal regions of South America. They produce huge populations of certain kinds of fish like anchovies, and then animals that eat these fish like certain kinds of cormorants. They are the beneficiaries of this kind of a phenomenon. But then, during an El Nino year, this phenomenon breaks down. The cold ocean waters are no longer being pulled up along with all their nutrients. Anchovy populations plummet, and then the cormorants that feed on them also decline in numbers. But it's not limited to this single kind of a phenomenon. The weather patterns around the world change during El Nino years. In North America, for example, both the Pacific Northwest and Atlantic Maritime Canada become warmer. In contrast, the southeastern part of North America gets cooler and wetter, and the Southwest also experiences wetter conditions during this time. Let's look at several graphics generated by the National Oceanic and Atmospheric Administration. Several of the images I've shown you in this program, in fact, have come from them, and I've also used their images in other programs. They have, by the way, a website which is well worth your while to check out for different sorts of views of Earth phenomena like these. If we look at this particular one, notice that it's of the planet in winter. And notice that northern parts of North America are characterized by warmer conditions, whereas the southeastern part of North America is characterized by wetter conditions. Notice also that a huge swath of the tropical Pacific experiences drier conditions during El Nino years. Now, in the summer, in contrast, the patterns are quite a bit different. You have a drier area appearing in Central America and northern South America, a drier area in India, but also you continue to have a drier swath through the tropical Pacific and through much of eastern Australia. Some of these regions in the tropical Pacific around New Guinea and northern Australia are typically tropical rainforests, so drier conditions there is really quite notable. So let's summarize. There is this interaction that occurs between the oceans and the atmosphere. Wind affects ocean currents, and heat from the ocean affects atmospheric circulation. The El Nino phenomenon, ENSO, is responsible for much of the Earth's climatic variation. When the trade winds weaken, the warm waters that are normally bottled up in the western Pacific flow eastward, and a whole cascade of events occurs that changes global climate. Let's turn our attention specifically to water resources. Let's begin by considering how much of the world's water is fresh water as opposed to how much is salt water. As it turns out, most is salt water. 97% in fact. And salt water, seawater, is quite salty. We're talking about 35 parts per thousand, or in other words, 3.5% of the water is salty. Now, even so-called fresh water does have some chemicals dissolved in it in varying amounts depending upon a variety of factors that we'll talk about. But it doesn't have that enormous concentration of sodium chloride and several other salts that are also found in seawater. Things like potassium chloride and calcium chloride and magnesium chloride, all those things are present in seawater. Here's a slide that summarizes all that while we look at still another view of the coast of Rhode Island. Make note here of some of those other kinds of materials that are dissolved in fresh water, like nitrates and phosphates and iron, potassium, calcium. Now let's consider how it is that water circulates about the planet in a series of phenomena generally referred to as the hydrologic cycle. Let's start with water as it exists on the surface of the Earth. It can be present in open bodies of water like the ocean or rivers or lakes. It can be present in wetlands like swamps and marshes. And it's also present in the uplands. It's present in soil, in between rocks, and it also can freeze on the high slopes of mountains. So we have quite a bit of water on the surface of the Earth. And this, in response to the presence of solar energy, evaporates and winds up going back into the atmosphere as water vapor. It accumulates there and forms clouds. And when enough water vapor accumulates in those clouds and it is exposed to cooler conditions, that water vapor is going to condense into droplets and come back down as precipitation. If conditions are above freezing, it will come down as rain. If they are below freezing, then it will come down as snow or sleet or something like that. So it's a fairly simple chain of events. Water on the surface of the Earth evaporates into the atmosphere, and then it condenses and comes back down again. Now, Some of the water on the surface of the earth is going to percolate through the soil and accumulate between layers of rock, accumulate underground in what is referred to as groundwater. And once it is in groundwater, it can stay there for a long time, although it can also exit by human activities like pumping from wells, or in places where the groundwater intersects the surface, it might again come out. So let's consider some of these terms associated with the hydrologic cycle. Surface water refers to open water on the surface of the land. And as I said, we can be talking about any kind of open body of water, but also things like swamps and marshes. Swamps, by the way, are wet areas that are vegetated by trees, whereas marshes are wet areas that are vegetated by herbaceous plants. Runoff refers to water that runs off the land into some kind of surface water. Groundwater is that water that accumulates below the surface, generally above some layer of rock which is impervious to its movement. Generally speaking, water will move through the soil and continue to percolate downward due to gravity until it reaches a layer of impervious material. And from there, it can move along that until it can again be discharged into rivers and lakes. There are so-called recharge areas, areas that supply groundwater, and discharge areas where water that's in the ground can make it back onto the surface again, surface water, and so on. Groundwater is replenished by precipitation. Oftentimes, wetlands like marshes and swamps can act as recharge areas, but not necessarily. It's not always quite that simple. Another term that relates to the hydrologic cycle is the watershed. Watershed is a geographic region that supplies water to a river system. So all of the tributaries of a river, all the little streamlets and so on, and assorted other wetlands that eventually feed into a major river, that's referred to as a watershed. The major river will then find its way to the ocean. One last term is that of the aquifer, and that is a space in porous layer of rock, or some kind of porous layer where groundwater can accumulate. It's not quite an underground lake, although it's sometimes described like that, but it is water that fills up all available spaces within an underground location, some kind of porous location. Now here's a map that shows where all that water comes from. In the United States, you'll see that the southeastern U.S. tends to be the wettest part, along with the Pacific Northwest. And the East in general is wetter than the West. The driest regions are in the southwestern part of the United States, although much of the area of the Great Plains is also rather dry. Now, one last topic for today concerns that of human use, how it is that people use that relatively small amount of fresh water that's available. People use it, as you see in this picture here, for agriculture. Now this is a vineyard, and in the foreground you're seeing olive trees. These are both crops which are often grown in more arid kinds of conditions, and you notice that except for the crops themselves, the rest of the landscape is pretty brown. So the only way these things can be grown here is via irrigation. And so agriculture can be a major drain on water supplies in these kinds of areas. We might also use them for municipal kinds of uses, household uses. Cities can be major consumers of water, like downtown San Francisco here. All the people who live in all those buildings all need to use water. And also, urban areas and also areas outside of the city can have industry. And industrial uses, especially certain kinds of industrial uses, can also use a lot of water. Think in terms of nuclear power plants requiring cooling water in order to keep them from melting down, like we saw happen in Japan a couple of years ago. Other kinds of industries use water as part of their industrial processes. So we can summarize these uses in this slide here. So human uses can be divided into agricultural, industrial, and domestic municipal kinds of uses. Notice in the background of this picture, however, that stone bridge. That's an old 19th century bridge, and it raises the issue of how long people have been associated with using water resources for things other than just drinking it. This is a bridge across the Blackstone River, which was just about the first industrial river in the nation. It flows through eastern Massachusetts and Rhode Island. Much of our country's textile industry was born here in the early to middle years of the 19th century, and this river was heavily used to generate power, water power, which was then used to run the textile mills.